All right. When you know the cross-section for a volume of a solid, or the cross-section of a solid, so I need your attention up here, please. These are not regions that are being rotated around an axis. This is, the problem is actually just giving you what the solid is made of. It's giving you usually some information about the base of the solid, and then it's giving you the cross-section. So from the last 2 days, instead of having to determine what the cross-section is, so remember cross-section, when I say that, what I mean is if you take the solid, you slice through it, the cross-section is the shape that you see. So when we had a disk, you would see a solid circle, a full circle, so therefore we were integrating the area of that circle to get the volume. When you had a washer, you saw a circle with a smaller circle cut out. So that's why you were taking the area of the larger circle minus the area of the smaller circle. But again, you were integrating the area of that washer to get the volume of the solid. Here, you don't have to determine what the cross-section is. The problem tells you what it is. So it'll tell you the cross-section is a square, the cross-section is an equilateral triangle, the cross-section is a rectangle, whatever it might be. Now you still have to figure out how to set up the area formula for the cross-section, but it tells you what it is. And again, what you want to keep in mind, or I guess the concept you need to understand, is to find a volume, you are integrating the area of the cross-section. So you're integrating the area of whatever shape it is. So before it was circles with both discs and washers, here it might be something different. So starting just out with an example, we have, and these I would say I would highly recommend. You don't need to draw them, and I would recommend not trying to draw them. Because, for example, like this is talking about the base being a circle and then equilateral triangles coming up off of the circle. So these would be much more difficult, in my opinion, to try to draw, and you don't need to do that. What you need to know is the cross-section and find the area formula for it. So here we have this figure. This is the solid we're going to be finding the volume of, and it has a circular base of radius 1. So what I have included here, or I included kind of a graph of the base region. So if the circle is of radius 1, I can let it be centered at the origin to have an equation for that circle. So maybe you want to make a note of this. I think in the practice problems there's one question that talks about a circular region. So just remember that the equation of a circle, you wouldn't have to remember this, by the way, for the AP test. You wouldn't have to just come up with the equation of a circle. I'm just giving you this for the practice that's out of the book. So circles have the equation x minus h quantity squared plus y minus k quantity squared equals r squared, where hk is the center and then r is the radius. So if we're given the radius of the circle is 1, I'm letting it be centered at the origin so that h and k are both 0. And that's where the equation of the circle is coming from, x squared plus y squared equals 1. So this is our base region, and we have the equation for it. And then it says cross-sections perpendicular to the base are equilateral triangles. So you can see what the solid looks like, but to kind of picture this, anywhere on this circle, you would have, like if I draw this here, this would be the base of an equilateral triangle. So I have a triangle coming like off of the paper. So equilateral triangle is coming up off of this. So the base of that triangle would be on the circle. Typically, you are going to have the base of whatever your shape is, the base be perpendicular to the x-axis so that you can integrate with respect to x. Unless the problem specifically tells you unless it tells you specifically it's perpendicular to the y-axis. So it'll tell you when you need to have it in terms of y, basically. So The cross sections are equilateral triangles. Find the volume of the solid. So here's how you work through these. Before we had to determine, do we have a disk, do we have a washer, and then we had to find the area of that circle by finding the radius, because area of a circle was pi r squared. Here, since we are told that the cross section is an equilateral triangle, this is what we're finding the area of. So area of the equilateral triangle So I'm just going to draw a triangle. This, if I sliced through this solid, this is the shape that I would see. And I need to come up with a formula for the area of that triangle with respect to x. And it will involve using the equation I have for that circular base. Okay, but where to start is say, okay, this is the cross section. I know to find the area of a triangle, I need to know what 1/2 times the base times the height is. So what I need is the base and the height with respect to x. So how to do that, what I'm going to write here for this circle, I'm just going to write, so I don't have to keep moving my paper up and down, the equation of that circle was x squared plus y squared equals 1. Okay, so from here, I'm going to focus on, I need an expression for the base in terms of x and an expression for the height in terms of x. I'm going to start with the base because the base of my triangle is actually on this circle. And what I do know here is anywhere I draw this, because the circle is centered at the origin, and this happens a lot when you have circles or even if you have ellipses, the distance from the x-axis to here, as well as the distance from the x-axis to here, those two distances are the same. And this distance, if you think again top minus bottom, would be whatever the y value is at that point. So this distance, I could just say, is the y value at whatever this point is. And that would make this distance here y as well. Now I know I'm writing y, I'm not in terms of x yet, but I have a way using this equation to get y in terms of x. For right now though, what I'm going to say is when I look at my equilateral triangle, this tells me the base has a length of 2y. So I can say this base, because it's on that circle, is 2y. And I'll write it in terms of x in a moment. It's easier at this point if you keep it in terms of y, and you'll see why as we go through this. Okay, now to find the height, so I also need an expression for the height. How would I get that knowing that this triangle is equilateral? How'd you get that? Okay, so equilateral triangle, this is 60. So basically equilateral triangle, when I draw in that altitude, what I've created is two 30, 60, 90 triangles. So I'm just going to show this. This is remembering some geometry here. Okay, now for each 30, 60, 90 triangle, the base of that 30, 60, 90 is just y, because it would be half of this. And if you remember special right triangles, if the short side is y, the long side, which would be the height, is the square root of 3 times the short side. If you don't remember, I'm explaining it to you now. And then the hypotenuse would be 2 times the length of the short side. But that allows us to find our height. You could also, you know that this side here would also be 2y because it would be the same as the base. All three sides of the equilateral triangle are the same. You could use Pythagorean theorem to figure this out as well. So you wouldn't exactly have to remember the 30, 60, 90. You'd have to be able to set this up enough using Pythagorean theorem to get this. So the height would be this y times the square root of 3, or square root of 3 times y. So I'm going to write this right now in terms of y. I still need to get it in terms of x. We'll get there. But this means the area of that equilateral triangle is 1/2 times the base is 2y times the height is y times the square root of 3. And I can simplify this. The 1/2 and the 2 will cancel out. So I end up getting y squared times the square root of 3. Now, it's not in terms of x, but look at the equation of the circle. I should be able to get an expression that I can substitute in for y squared. That's in terms of x. Yeah, so if I solve this for y squared is 1 minus x squared. I can substitute that in for the y squared here. Okay, and then it's in terms of x. So overall, the area of that cross-section with respect to x is going to be, I'm going to write the square root of 3 in front, the square root of 3 times the quantity 1 minus x squared. Could what? You could. You wouldn't have to. I would probably leave it out because it's a coefficient, you can take it out of the integral when we have to integrate. Okay, so questions at this point, how we got this. Okay, then, here's how you find the volume. This is the most difficult part to come up with because now the volume of that solid, I wrote that kind of weird. Volume is just integrating the area of a cross-section. So this means you are taking the integral of the area of that equilateral triangle. You do have to know your limits of integration, though. What would we use for our limits of integration? -1 to 1. Okay, our circle, the x values extend from -1 to 1. So we're integrating from -1 to 1 the area of the equilateral triangle, which is the square root of 3 times the quantity 1 minus x squared dx. Now, some hints to make this a little bit easier, not that you would have to do this. One thing, because of the circle being centered at the origin, I could also, rather than going from -1 to 1, I could just go from 0 to 1 and then double it. Okay, that helps you in the sense that one of your limits is 0, and that's easier to substitute in after you take the antiderivative. So you don't have to do that. I'm just explaining you could. I could say this is equivalent to 2 times the integral from 0 to 1 of the square root of 3 times 1 minus x squared. Okay, you don't have to do that. You can. And that's because from 0 to 1, that half of the circle is the same as the half on the side from -1 to 0. They would not, but it would make solving the integral easier, or evaluating the antiderivative easier. And then when you're taking the antiderivative, you could do this beforehand or even while you're taking the antiderivative. This coefficient, square root of 3, can just be taken out. So I could include that. So you're not finding the antiderivative of the square root of 3. That's just a coefficient. So I really have 2 square root 3 and then integral from 0 to 1 of 1 minus x squared. So you're just finding the antiderivative of 1 minus x squared. So I'm going to keep the 2 square root 3 out front. What is the antiderivative for 1 minus x squared? And then I can evaluate that from 0 to 1. And here, as you can see, I really don't even need to plug in 0. If I plug in 0, I'm just going to get 0. So that's why this just makes it a little simpler. All I really need to do is substitute in 1. So I have 2 square root 3 times, if I substitute in 1, I have 1 minus 1/3. So I have 2/3, and then minus 0 if I did plug in 0. But that leaves my volume as being 4 square root 3 over 3, or 4/3 square root 3. And that is your volume. Makes you think. Yeah. Yes, Lydia.
No, the Russian space industry.
I know.